Morning, everybody. So this is going to be our tutorial on blackbody radiation, a mode of heat transfer that comes about simply because an object has temperature. And that's one of the fundamental rules of physics. If something has temperature, and all things must have temperature, then they are radiating energy at a particular wavelength, or I should say range of wavelengths. So I'm going to just start off with a very simple little video. It's not even much to see. Something we've seen before when we were doing the electromagnetic spectrum. Okay, it's just a thermal image of the human body. Okay, so in other words, if you look at the human body in visible light, you will see, well, the skin, right, hair, etc. But if you look at the human body in infrared, that's what these cameras are, right? We've seen them before. They're fairly standard now. You see that we glow. So if this is a pitch black room surrounding right there, we see our body glows, and you can give them false colors. The red, I believe, means warmer. The blue means colder. Is that our body is glowing, and it's glowing in infrared radiation. And the reason for that is because we have a temperature. And like I said earlier, all bodies have temperature. Excuse me. However, ours is generally warmer than a lot of, let's say, non-mammals. So we want to understand what determines the type of radiation that our body does. And then in the process, we're going to understand ultimately how the Earth's climate is affected by this radiation. Okay, so let's go back to the notes. So from the thermography, we can see that everyday objects emit energy in the form of electromagnetic radiation. In this case, I'm going to put in parentheses infrared, right? Most objects emit infrared radiation. However, if the objects were extremely hot, let's say like a light bulb or a star, then they would emit it in a wide range of wavelengths, most of which would fall into the visible part of the spectrum. Okay, so the reason the sun appears visible to our eyes and a fire does, or a light bulb, is because it's really, really hot, much more hot than a typical, let's say, organism. So in other words, they would glow in a way that the naked eye can see. Okay, so we're going to look at the blackbody curve, something we looked at way back when we were introduced Planck's law. When Planck tried to reproduce this curve that physicists could not using classical theory, he came up with a very startling discovery, right, that energy can be quantized. Well, we're not going to worry about that right here. We just want to understand, ultimately, if we've got intensity here and we've got wavelength here, how can we predict what that peak intensity is going to be? Excuse me, at what wavelength is the peak going to be? And we see this is the sun's spectrum, and sun's surface temperature is about 6,000 K. And then here's something that's slightly cooler. And notice that graph drops tremendously. It shifts to the right, okay, shifts towards a longer wavelength, and it spreads out. Well, it's just not as much intensity, I guess I should say. I shouldn't say it spreads out more. And so if we get to the human body, which would be around here, you see that our wavelength is moving. Not that you remember, but right here is Roy G. Biv. So that's the visible part of the spectrum. But as we shift to lower and lower temperatures, the peak shifts to the right. And so we're getting into the infrared. And ultimately, you could argue we get into the microwave part of the background. Okay. Or, excuse me, of the spectrum. So this is the law that relates wavelength to temperature. It's fairly straightforward. It's called Venns law. All right, one of those physicists, probably German or Austrian from the 19th century. And Venns law holds for a black body. And a black body is just the physics name for a perfect emitter of a radiation. So whatever radiation it has, it does not trap in, it just continually emits. And so Venns law basically says that lambda, and we can put a peak, I'm not going to write the word peak there, but it is peak wavelength, is simply equal to a constant. So I'm not going to give the constant a name, it's not super important, but here is the value, 2.90 times 10 to the negative 3 divided by temperature. Now there should be units with that constant, right? So it would make sense that that's going to be meters per Kelvin. And temperature has to be an absolute, right? So meters per Kelvin, I should say meter kelvins, divided by kelvins gives us a wavelength in meters. Okay, and lambda is the peak wavelength. All right, and its wavelength to the temperature. So that's the important thing here, is anything with temperature is going to emit radiation, and Venns' law gives us a peak wavelength. So in example one, if we were in class, I'd show you something with a spectrometer where I can look at the output of a light bulb. I don't have that information off the top of my head, so I'm going to skip that one. So let's go to the peak wavelength for a human body, where our basal temperature is 37 Celsius. So the only troubling thing about this, or potentially troubling thing about this, is we got to make sure we're in the right temperature. So we want to convert that to Kelvin, so that's going to be 310 Kelvin. So now we can just say wavelength is a 2.90 times 10 to the negative 3 divided by 310, and that's going to give us a small number, but not as small as, well, not that you expect anything, negative 6 meters. Did I do that math right? Yep. So that's going to be about 9.3 micrometers. And while that's small, that's, well, not even close to being in the visible part of the spectrum. That's, as we said earlier, in the infrared. Now the sun, on the other hand, right, its peak wavelength as measured by spectrometer would be about 503 nanometers. So we could ask, what's the temperature at its surface? So we just turn things around, and temperature is going to be equal to the 2.90 times 10 to the negative 3. And then I got to make sure I convert 503 nanometers to meters. And then I'm going to get around, I'm just going to round here, 5,800 Kelvin. Okay, so that's very, very important. And so by looking at the light coming from any star, we can infer what its temperature is. And based on its luminosity and distance, we can figure out how big it is. And there's a lot we can learn from a star from that wavelength, or from that blackbody spectrum. This is really, really important, along with spectral lines. All right, so let's now start applying this to the Sun/Earth system. Okay, hold on one second. I got 7 minutes. So, solar radiation. The sun is essentially a black body, and we just said it has an outer temperature of around 5,800 Kelvin. As such, it emits radiation at a certain rate. And so we want to quantify that. And there's two different measures of the sun's output, and you got to make sure you're careful to distinguish that. All right, one is simply power, right? The rate at which you give off energy is by definition power, and we can talk about what's the power output at the sun's surface. And then, more relevant to the Earth, we want to look at its intensity by the time it reaches us. In other words, the idea is, if here's the sun, and, well, let me make the sun bigger, and here's the Earth quite a bit away, that energy is spreading out. Okay, so that power is radiating in all directions, and so we only get a tiny little chunk of that, and so we want to be able to quantify that. So the first one is the most important equation of this, and it's called Stefan-Boltzmann's law. There's Boltzmann again from kinetic theory. Okay, Stefan was another physicist. And they give an equation for power output of a radiating body. Okay, so basically it's simply this. Power equals, we have two constants. We have a little epsilon, we have a sigma, lowercase sigma, and then we have A, and then the most important part, there's the temperature, to the fourth power. So you see that the power output of any body goes by the fourth power of the temperature. So sigma is called Stefan-Boltzmann's, I'm just going to call SB constant. Don't confuse that with Boltzmann's constant. And that's a value of 5.67 times 10 to the negative 8th units, right? So if I work that out, it's not in your reference tables because it's more of an IB thing, and I don't have the IB constants, but we can work out it's going to be equal to watts per meter squared per Kelvin to the fourth. Okay, area is surface, or A is surface area. Okay, so that's the surface area usually of a sphere. And epsilon is called emissivity. Okay, and it's a constant. It's just a number. And it's basically how good of an emitter, how good of a black body it is. So the sun, we said, is a perfect black body, so its emissivity is 1. And if you give off no radiation, you're really bad. Generally, like metals are, or white objects are, you have an emissivity of 0. So most objects fall somewhere between the two, where most of the problems we're going to treat the emissivity as something closer to 1. Okay, so let's ask a question. What is the power output of the sun in watts, assuming it's a perfect emitter, and we know that its size is as given? All right, so it's a fairly simple issue of plugging in the numbers. Okay, so for epsilon, we're going to put in 1. For Stefan-Boltzmann's constant, 5.67 times 10 to the negative 8th. That just rolls off the tongue. Okay, the area is the surface area. So you got to know the surface area of a sphere. That's going to be 4 pi r squared. So 7 times 10 to the 8th quantity squared. And then the big thing, the temperature to the 4th. And we're going to go with the surface temperature of 5,800 to the 4th power. And you can see 5,800 to the 4th power, that's going to give us a really large number besides these. Okay, so you plug in the numbers and you get a whopping 4 times 10 to the 26th watts. Okay, so the sun's putting out, well, I don't even know what that number is, basically 10 trillion joules a second because of that fusion process. Now, for us, we got to look at intensity. All right, so I have a little schematic down here to just understand how any body, as it radiates, it spreads out, the radiation spreads out, and you can see as the distance changes, the area changes by the square of that distance. And in fact, that gives us one of the more important rules in radiation physics. That's the inverse square law, and that's not the equation I can put here, but we can see that I, which is intensity, is proportional to 1 over r squared. Okay, so both curricula want you to understand that, but that's beyond that, we don't have to do anything. So, as I said here, the power calculated above is surface, but by the time it reaches the Earth, it has spread out tremendously. In other words, the Earth does not feel the entire power output of the sun, but rather a small chunk of it. Okay, so we can relate intensity to power very simply. Intensity, by definition, is the rate at which you're outputting divided by the area of the sphere of radiation that you have emitted. So, again, let me just do a little schematic. If here this dot represents the sun, and I'm a certain distance away from an r, then that radiation has spread out in a sphere like that, and we want that surface area. If we go further away, it's even more spread out so that the intensity is less. And the units are going to be watts per square meter. And that's an important number when we eventually get back to climate change and weather and talk about those forcings. We look at all the forcings, we look at their intensities in watts per square meter, and then the net result tells us how things are going to change on the Earth. Okay, so let's finish up with an example. So what is the intensity of the Earth's radiation when it reaches the top of our Earth's atmosphere? Which, in other words, the Earth is this far away from the sun on average. So we can say that the intensity is, by definition, the power output of the sun divided by the, not the area of the sun, and it's not the area of the Earth, and it's when we start looking at energy emitted versus energy absorbed, those areas, understanding the difference between the object emitting it and the object absorbing it, we have to be careful. So this is the area, I'm not going to put this Earth, because it's not the Earth's surface area. Okay, it's the surface area of that sphere of radiation surrounding the sun at that distance. So anyway, this is the roughly 4 times 10 to the 26th watts, and then this is going to be 4 pi, and then the 149 times 10 to the 9th meters quantity squared. All right, punch out the numbers, and you get a very important number called the solar constant, S. And I've been using approximate numbers. It's similar to this. I don't think we need to know the exact value. We'll modify it when we get into greenhouse effect. But the solar constant S is 1,420 watts per square meter. So that's the intensity that the Earth gets if it's facing directly on. Now, since the Earth tilts on its axis, this number varies at latitude, but we're not going to worry about that right now. We're just getting a ballpark figure of roughly how much energy we're getting from the sun. Why are we getting this value? Well, A, we're that far away. B, the sun is its size. And C, most importantly, the sun has that temperature. And that surface temperature ultimately is what's going to drive things. Then we can eventually ask, what's the power input for the part of the Earth facing the sun? In other words, if I want to know what rate are we actually absorbing energy, then I'd turn things around and I'd say the power, and I'll just call it the Earth, is the intensity that we calculated above times that area facing, the area of the Earth facing it. So we'll have more to say about that, like I said, when we go over the greenhouse effect. So just to finish up, the intensity at the top of the atmosphere is not the same as the intensity that reaches the surface of the Earth. So if we eventually want to understand what temperature should the Earth be because we're this certain distance away from the